Okay, guys. So today I'm going to talk a little bit about the history of deep learning. Everybody's got crazy about like deep learning is changing everything that we know. And I promise you, this is not just a history lesson. You will know one most important thing that you will always require in any data science project that you will ever do. So people always tell me, okay, what do you do? I say I work as a data scientist, I do machine learning, and they're like, wow, exciting new field. And I say, it's not really new. I have been doing this ever since I got out of college. At that time, it was a blue-collar job. We used to call it data mining. And it is actually much older than most of the new technologies that we are used to. It is older than web. It is older than internet, definitely. It's also older than the company where I spend most of the time, SPSS, like one of the original data science company was founded in way back in 60s. And it still exists. And most of the algorithms that is currently dominating everything were invented much before that. Many of them actually almost 200 years back. So what is it that has changed? I mean, is it really all the hype, or there is something really fundamentally magnificent that is going on? And I can give a sneak preview that it is a combination of both. So hey. Okay, sorry for that. Okay, sorry for that. I will switch manually. So deep learning, you can find in everything that is currently dominating. Like, for example, is the orange good or bad? I mean, instead of using humans, let's use a deep learning algorithm that can do it. It's dominating self-driving car. Like it's one of the fundamental technology that as in use in image recognition, as well as do something really amazing like in the creative world, like create a painting as Van Gogh would have drawn that. And it can even be used to, let's say, write the poems. That's something you can probably say human could have written. Quite not yet there, but something that is really getting as close to human intelligence as people can think about. That last project, by the way, was done by me. So a little bit of humble brag, trying to teach machine learning to write poems. And if you ever seen anything in the media, then media is all going crazy that this is something like the great AI consciousness or something big is happening. But is that really the case? Now, is this something that we have suddenly discovered yesterday or maybe today? I mean, it all happened in the last couple of years. So it feels like we have suddenly discovered a huge eureka moment. Now, if you will look at the history and try to find out who was the first data scientist in the world, then you may have to go all the way back to 1850s. The first data scientist in the world was a woman, a very famous one, whom you probably heard, Florence Nightingale, the same person. And she has collected the data for the British Army, and she has plotted the chart using the simple analysis of basically doing the like the regression analysis about how many soldiers are dying in battle versus non-battle. And she had done year on year, so she collected almost 5 years of data. And if you can see the chart, then the yellow is the color of soldiers which are dying in the battle, and green is which they are dying outside of the battle, like due to health issues. And this was a fascinating chart, which she did without Tableau or ClickView or Matplotlib. And this was so, it is so not just a good insight that, people say you have to tell a story with the data. You tell, what is data science? Telling a story with the data. This has fundamentally changed every single army in the world, because that created the world's first sanitation department in the army. She showed that more soldiers die because of lack of sanitation than actual warfare. So this actually saved millions of lives. And she was probably the first data scientist. And we always talk women in technology, they were already there. And so was the first analytics programmer who actually preceded her in 1830s. who created a first analytics program by trying to code the data bits. She unfortunately doesn't get as much credit as her boss, Charles Babbage, whoever says invented first computer, but she was the one who actually saw the power of putting the data in and then getting the analytics out. But if you will ask me, then my favorite person whom I found in my reading who rarely gets so much of credit for really inventing big data and data science is this guy. Yes, that's Benjamin Franklin, and that is an actual quote which he said in 1750s. Today, that quote is so self-evident that every executive knows it. But imagine somebody being a visionary and saying that in the 1750s. Now, Benjamin Franklin was an innovator who first did the concept of quantified self, something like measuring everything that he's doing in the charts, like how much he has eating, how much drinks he had, when he goes to sleep, when he wakes up, how much time is spent studying, reading, writing, walking. Fitbit, he was the first guy who invented Fitbit. And it was much beyond that because he was tracking effectiveness and mindfulness every single day and trying to improve himself. So if you ever thought like Apple Watch or Fitbit, then this was the guy who did it. If you will ever Google the chart, they are really good because he's keeping the notes like don't drink too much. He put a goal for how much he should drink wine, and then he will track on the average weekly basis. Now, that was not all. He probably invented world's first machine learning algorithm. He was a postmaster general of US, and you had to deliver the post to everybody, right? So what he did was something very ingenious. He put an odometer at the front of the horse carriage and asked his postman to measure the number of miles that they will go to deliver the post to each location. And then he used that data to find what is the shortest path in order to deliver all the posts on any given day based on the number of locations that you need to travel. Sounds familiar? Google Maps. That's exactly that they did. And if you think that was an easy thing to come up with, it was not, because he was trying to solve a problem not using geometry, not using mathematics, but by using data. He just collected all the data that each mailman is actually traveling each day, and they just used that data to find the shortest path. Probably one of the best paper that he has written was in 1750s was on United States Census and how government should make a policy by looking at the birth rate and the death rate and the population. And he was probably the guy because we have a census every 10 years in the US. And the biggest credit for this was not what he actually did, but he actually inspired a lot of physicists, statisticians, and mathematicians at the time to measure everything. The simple thing was if you cannot measure it, you cannot improve it. So that word data-driven approach was actually invented because of him. So everything that we use for fireplace, centimeter scale, horsepower, Kelvin, all those statistical measure came from that. So I would say like he's the guy who actually invented big data, and that made all these things possible, who really understood the fundamentals of data. Now, it's like, okay, that's all fine, but we all know like artificial intelligence started with Alan Turing, and that's true. The current form of human-like intelligence was popularized by Alan Turing in his 1950s paper. That was one of the foundational paper, and it kind of changed everybody at the time that, we are going to see all this, robots flying very soon, if you have seen the Euphorian movies at the time. And very soon, right here in New York, in 1957, they invented neural network. Believe it or not, it's not new. That's why I told you, neural networks regression, it's pretty old. So the first architecture of neural network was invented in 57. And here in the New York, in the World Trade Fair, IBM actually built a machine where they said this is the world's first AI computer. And if you closely read the New York Times headline, it reads that machine which learns by doing things. Now, that's actually even beyond deep learning. That's like reinforcement learning. You're talking like a real human-like intelligence. But there was like all euphoria. You know, we cracked the cookie in 1950s. So that AI Spring was then, I mean, the curiosity is like, okay, that's like what, 60 years, 65, 70 years? What happened? I mean, if things were so great at the time, then what is it that we were not able to solve the problem for so long? And what has happened in last 3, 4, 5 years that we got solve it like this? What's that magic sauce? That AI Spring, which Alan Turing started in 50s, unfortunately he died soon after, otherwise he would have figured out the problem, was actually followed by AI Winter. This slide is like this because there is actually nothing happened for next 50 odd years. Okay. So, and AI Winter is not the term I invented. It's a very technical term. I mean, if you know neural network, then in neural network there is a forward pass and there is a back propagation. So nobody invented back propagation for a long time. So the research, money, everything was gone. But anyways, it was all followed by a deep, deep kind of a frozen state, like nothing was happening. And then something happened. Now, before I tell you what happened, if there is one thing that you will probably need to know about data science, then it is this. It's probably you have seen it, some of you not. So I don't know, like I will quickly explain it. So in case of like any data science thing, we have this trade-off between what we call bias and variance. Like we can build a model that is really good on the data set we got. So we can either overfit it, or we can reduce the error and we can try to generalize it. So there is that generalization gap. So while we can keep on minimizing the training set, it may not actually work so well in real life. Now, to put it in plain English, what it means that I can build a very good algorithm on the data I have, but that's not very useful because the algorithm has to work on the data that it has not seen, right? So that's the basic fundamental of any predictive model that you will do. And it's just a fancy mathematician's way of putting that on a chart. And keep that in mind as we will go forward. So what was happening for last 50 odd years was like all mathematicians, people, they were trying to solve this problem by actually figuring out the feature for each of them. Now here I'm focusing on one really fundamental problem of image recognition or computer vision. This is about what is inside an image. And this is a really big problem. Believe it or not, people thought this was a very simple thing. In 1960s, around same AI Spring time, when an MIT professor gave this as a summer assignment to a student. You know MIT, everybody's smart. Hey, figure out computer vision in your summer assignment in 1 month. And they thought they could do it. But nobody did it. Now the reason behind that, I mean, forget all this algorithm and all, was that they were trying to fit a model into each of the single image. That is what every physician was trying to do. The technical term for that is, okay, I have a face, then I have a hair, then I have eyes, then I have nose. Like figure out the structure within the image. That's what everybody was doing. So if I have, let's say, dog, then dog is an animal, then he's a mammal, then he has hair, and he's a dog. So that's what everybody was trying to do. It was trying to fit everything in an inferential model, like what inference I can draw from a given image. I probably you don't have to worry if it is Bayesian or not. I mention it primarily here because that was the preferred choice of algorithm for a long time for a statistician to solve an image recognition problem. It's an interesting thing because probably you already know that we all use neural networks now for doing deep learning. So that is what everybody was trying to do. But is that how human brain works? Just ask yourself. Is that how humans learn how to recognize images? I mean, look at a baby and how the baby learns to understand which object is what. Now that actually happens because in the first 6 months or first 9 months, when the baby is born, thousands of images flash in front of a baby. And based on the images that we see, we tend to identify the objects. It is not like we over-specialize the object. In fact, if you will try to see from a mindset of a baby's eyes, then the baby's brain is not so well developed to actually recognize fine feature. They, for example, when they see the face, they normally see it very rounded, not all the finer object. That's why the cartoons are very popular with the kids, because they are made with the simple features. To put that on that chart, if you will show a baby, let us say orange and an orange color ball, then they will not know the difference. But that's okay. That's how human brain learns. We tend to have this generalization gap in our visual cortex, that we see an object and we find something similar to it and we recognize it. And as we go learn more and more, we'll see, okay, that's orange, it has finer thing, and the ball doesn't. So we learn by making those mistakes and drawing similarities. Now that may seem like a very simple observation, but that was of something really fundamental that changed, I think, the history of how this problem is being solved. So the focus then shifted, that instead of trying to solve the deep learning visual recognition problem from modeling or finding the big, huge, really complex algorithm, to data, to lots and lots of data. So just as a human baby learns, so if you have a baby who has never seen, let's say, grows up in Alaska and who has never seen a flower, I don't know if there is a flowers in Alaska, but I mean, the baby wouldn't recognize it because that image never flashed on it. On the same way, the only way you can make somebody recognize an object is to flash lots of things on it. So what happened was something really interesting. Is the problem is that you already know is that we just can't get the data. You know, and now, I mean, if there is one thing that every single data scientist struggle about, and except if they are working in Google or maybe Apple, is that nobody has enough data to do the modeling. So it's like a catch-22 situation. Okay, now we think maybe we need a lot of data to do image recognition, but then we don't get it. So what can be done? So this lady, which I think is one of the greatest data scientists in the world right now, her name is Fei-Fei Li. She was head of a Google Brain at that time, and she was also the head of Stanford's AI lab as well as Princeton AI lab. So she visited Princeton's university, and they said, listen, this is what, she met a couple of neuroscientists and said, this is what she's doing. And she came up with this idea that Google, which actually has all the data in the world, will just release all the images for free in the public domain. So, and they released millions of images. They called that project ImageNet in 2009. And everybody can use that ImageNet data set to try and build their model. Now, this is a fundamental shift. It is not just like trying to solve a problem with a different data set. What people were earlier doing were hundreds of images or hundreds of data points. That is how statisticians work. You know, I said I work for a company which was founded in the 60s. All statisticians work on few hundred rows, few thousand rows. Here we are talking millions and millions of rows. So while no new algorithms are invented in last 5 or 10 years, what has changed is this millions of rows, millions of data set that has been made available. So she made available this ImageNet data set, 10 million images, and that fundamentally changed the structure. So I will quickly go through what has done. Is like, in case of this massive ontology of a computer vision data set that is made available, the first problem was to curate the data. Now, this is something that very few people appreciate or even kind of tend to give importance to. One is like, you cannot get the data, but then you cannot get a good quality data. So, okay, you throw in these images, what good are the images if nobody tells me as a human if that image contains a dog or a cat? I mean, the machine cannot learn by itself, right? I have to pass some input to the machine, and only then machine will learn. So what happened was that they had to create this some kind of a structure similar to it that we can pass as a label to the machine. And in order to do this, like populate categories with thousands of images that they collected, got from the Google, they ran this project called Amazon Mechanical Turk. So around 50,000 workers from all over the world actually done crowdsourcing and manually identified each of the images, whether it is dog or the cat or the human or whatever they are doing in the image. Now, this is, as I said, is a most underappreciated effort because this is not an easy task. As you can imagine, imagine 50,000 workers voluntarily identifying images for internet. They are just donating their time, which the other could have spent on other valuable activities like watching YouTube or sending messages or text. So something that important, they sacrifice for doing this, and that's how the ImageNet project goes live. Now, why is it relevant to whatever you are doing today? Because every single data science project that you will do, you will be stuck with this problem. One, do you have the data? And second, do you have the enough data? Most data science project requires the data in tunes of millions of rows only, then things work really awesome. So if you think why Amazon or other algorithms work, because they have a lot of data. The second, which I said, is this quality of the data. Somebody can throw million rows of you, but you still need to add that human mind into it before you make a machine learn from that. Okay, and this is something that I even find it even today when I talk to executives. They have a notion that you give just the raw data and machine is a magic box and algorithm, it learns all by itself. No, that's not how it happens. You have to provide a very good label inside, and that's a human effort. So the right word is normally semi-supervised learning in order to do it. So ImageNet goes live. Those two logos is because, as I said, it's a combination of FLE, that's Google, that's Princeton, that's Stanford, just a bit of trivia. And they targeted at the scale, high resolution image set. That was the first time when Krzyzewski introduced the AlexNet model, which is like a deep learning model, and the error rate really plummeted. And after every single year, then everybody built a more and more sophisticated deep learning model. And as you can see, it is now last year at 2.3%. The most interesting part in that chart is that human error rate is 5%. So currently, the image recognition algorithms are actually better than the humans. So, and this is why people are spooking out about like, hey, that AI is getting too fast, too quick, too soon. Okay. But all this thing essentially happened very fast because of that one crazy idea. And this was not just limited to recognizing the images, but within the object detection, localization, like within, like, there is a person, car, helmet, and then you can actually take it to the next level. So if there is one thing that I would say you need to walk out of this history lesson, starting with Benjamin Franklin all the way, and that is this: the data sets and not the algorithms is the key to solving your most complex problems. People say you shouldn't be saying this because then it takes away all the salaries that data scientists make. People will not pay them 200K packages, but that's a fact. I like to say that the data science should be spelled as a data hyphenated science, because if you take away the data out of it, there is no science left. So that's one thing you'll know. So I think I'm out of time. I'll probably quickly take one thing about some of the interesting things that happened after ImageNet, which is that it definitely became a benchmark. It is now, the same idea is now used in medical resolution. So for example, in cancer detection, dental problems, tumor detection, pancreatic, blood sampling, and it is working amazingly. That is not just like recognizing cats and dogs anymore, but it is about preventing diseases. It's also about breakthrough in other areas of machine learning. Some of the most unexpected outcome, and this is what everybody was thinking here when I said deep learning, was that neural net became cool. As I said, with neural net is actually very old. It was invented, as I said, in 50s, the CNN architecture, convolutional neural net, which is precisely used, was invented by a Japanese guy in 70s and 80s, and they even built a model on the top of it, but they were like somewhere sitting in a dust. And they currently catch the frenzy of everything, and every year people are building more and more bigger and bigger nets. Now it's like thousands of layers. So that was a totally unexpected outcome, because that, if you remember that slide I showed you earlier, everybody was thinking Bayesian and other method. Nobody thought neural net could handle it. Now what that tells you is that data scientists are not so smart. They are just trial and error. So they will try 4 algorithms. Okay, now neural net is working, and then everybody jump onto it. So that's a cool part that I think is about that ImageNet. The second is the project has definitely moved on beyond object recognition. So instead of just recognizing, hey, there is this person here, now we can even recognize what they are doing. So it's like they are like person is stepping on a scale to add weight and ups and downs. So most of it then came like in this picture, there is not just a lady here, but everything that is happening. Now this was based on Microsoft Coco's caption data set, and in fact I have used that extensively in my work. So after seeing the success of Google, Microsoft did what they always did. They tried to copy it and release their own data set. So they created similar huge captioning data set, which was like not just describe an object, but what people are doing it. So like a lady in a pink dress is skiing. And now this is used to actually take it to the next level, where you can actually ask the question to the machine, learn-to-learn learning and other areas. But this is the fundamental strategic inflection point that I think will change it all. So on that note, this is not the end. It's not even the beginning of end, but it's end of the beginning. We are probably ending that long winter of last 250 years when you talk to actually about end of the beginning of the actual intelligence. So thanks guys.
Okay, so this is about data science and value creation. And to start, I did not plan my career to be a data scientist. I studied engineering. I studied programming a long time ago. Then I got a master's degree in business. And then the early 90s, started working for a hedge fund. And shortly after working there, I became director of quantitative analysis. So the closest thing in the 90s to a data science now is a quant guy. A quantitative analyst is a guy who works with tons of financial data sets and needs to act very fast on this information in order to generate value. And so my career has been basically in finance, and just recently I started this consulting firm where I have been doing work for some of these companies or entities. But let me explain how I evolved into a data scientist. So first, we need to understand that not all data scientists are created equal. And this is a little bit in line with what Fabio was saying. So taking surveys among people out there and other senior data scientists, there's some sort of consensus. There are 4 types of data scientists. You have the business data scientist, the creative data scientist, the developer, and the researcher data scientist. The core background is the same. It is machine learning, business, math and operational research, programming, statistics, and data visualization. The proportion is what changes. Now, in the vertical, we have a junior data scientist, a guy with probably some quantitative background and had done some Kaggle competitions and can work with some structured data sets. That same person can be a PhD, can be just a bachelor's degree, can not have any degree. And after a certain period of time, that person can evolve into a mid-level data scientist. I've seen a lot of people straight from PhDs going to this category because they have a PhD. And they know how to work with semi-structured data or structured data. Sometimes they know how to work with unstructured data. The senior person knows how to work with all kind of data sets, has large company experience, maybe some patents under the belt. The main distinction here is in this side we have data scientists are closer to the business world. And in the other side we have guys who are very theoretical. And they are not necessarily a good fit in an organization where the bottom line is money, but they may be very good developing, deep neural nets theory and image classification and distinguish a cat from a dog with 99% accuracy. So this is how I evolved into a data scientist. So 83, I started programming, started college engineering, lots of operational research, got a degree in 87, and I started to work straight in purely engineering projects. But it had a lot of operational research for industrial problems. So in 93, I finished an MBA with concentration in finance. And at that moment, the combination of engineering plus programming and statistics and all of that made me a quant. So there was not financial engineering master's degree or anything, but that sort of career path made you a natural quant. And I started working with neural nets very early on for, is there value here? Can we make better trading decisions using neural nets? And I was very disappointed for what came out of those experiments. But some things were good, decision trees to create master list of companies to go or long that needed a lot of human screening. So the lists were good. So 98 to 2008, I switched from this buy side to the sell side, working for AIG, Deutsche Bank. Ended up in Lehman Brothers, was a very good job. Unfortunately, the company collapsed, and they were very pioneering in the field of data science, although it wasn't called data science, it was called special opportunities. But the kind of background was more or less the background I had. Somebody who has all this technical background, but has proven track record monetizing these exotic data sets. I mean, I'm talking about weather or earthquake frequencies or data that has to do with potential failures of rockets at launch. How do you make money out of that? In 2008, after the collapse of Lehman, it's really hard to get back into finance because nobody is hiring, especially quants. Quants are blamed for everything that is happening at that point in time. But when I look at my career, then I realize, well, I'm just a data scientist because I've been doing all of this stuff, but it's not called data science. It's called something else. My code is not in GitHub or Bitbucket or any of that because when you develop code for these organizations, well, you keep it to yourself or for the organization. You're not going to be sharing this code with anybody. That's a key competitive advantage that your bank or your hedge fund has. So I had an idea of creating a search engine. I started to see that. My thinking was the following. I had developed a whole career in structured finance. And structured finance basically taking unstructured assets, wrapping them and making them structured and transferring them to the markets or holding them. So what I started to see in 2009 is that Google search engine and Bing and all of those guys were doing a very good work with structured data. But what happens with the unstructured data out there, like a tweet or an Instagram, a piece of a picture, a piece of music. And when I started to collect data, I basically wrote a bunch of scrapers. I started to see a tremendous growth in the structured part of the web compared to the structured part. So Yahoo, Bing, Google, all of those guys were designed when most of the information out there was structured, HTML content. If you remember, there used to be a webmaster who actually puts the content into a web page. But 2009, I realized, wait a second. We look at the time series. Unstructured is growing a lot faster than structured. By 2012, it's going to overtake the whole web. Who is indexing that. And the indexation is very difficult because you have to build image recognition to detect this is a dog, this is a cat, or sound, this is a jazz, this is whatever it is. So I did that. I built some prototypes and immediately applied for patents. So if you know a little bit of history, the algorithm that Google uses is called PageRank. So people say it's because of, Larry Page. Some people say it's because it's just ranked pages. Maybe it's a combination of both. But at that point in time, in 2009, I saw that there is a new form. The page is not the basic unit. It's content. So a tweet or an Instagram picture or whatever it is. So I came up with this algo called content rank. And actually, when you transfer all these schematics and prototypes to the lawyers, it goes translated into 11 different applications. So early on, I applied for this, raised a little bit of capital, and a little search engine trying to compete with the big guys. And this is a summary of what I'm going to show you. What happened with that is that eventually I did launch my search engine. It was you could access it through the web, and you have your iPhone app, your Android. But I think I was better data scientist than CEO. So a bunch of things happened, and at the end, all the algos were acquired by a hedge fund. That was in December 2015 when the patents were actually issued by the US government. And in 2015, I folded this company. A lot of very interesting things came out of it. I'm going to show you some. And I started this company I have right now, SGX Analytics, which is basically developing data science and data strategy projects for clients. So let's see if I can cover some of the things here, because there is a lot of materials trying to show almost 25 years worth of data science project in a short time. But I have used it for the design and launch of new financial products, to forecast movie and music royalties, to forecast earnings for companies that trade, and even for music composition. So this is very old, 1994. And this is an article in the Washington Post that talks about how this guy, I was young then and older now, was responsible for creating this amazing trade for the hedge fund. And actually what happens there is, again, data, So there is this thing called the Binomial Mold to price options. And it looks very much to some of the things you see nowadays in data science, when you start looking at decision trees and all of that. But basically, you could, back then, arbitrage prices from different banks. You ask for an option, let's say a knockout option. A knockout option was a very exotic type of option back then. Still, it is a little exotic now. And it's just a regular option with a bunch of constraints. And the thing is that they are priced with proprietary molds. So you ask Goldman Sachs, and they give you a quote. And you ask Bank of America, they give you another quote. Maybe similar. But this is the thing. If you just change the features a little bit, here and there and there, and you get these quotes, you could see that, if I buy this one, sell that one, and actually you write a program for that, you could end up with a risk-free position. And so these are some of the things I was doing then. But then that gave me the idea of start automating all of that. And a lot of statistics, and it's just a very simple calculation right here. So this is a real case, so you want to read it. So I basically wrote a program that was collecting all of these quotes for very sort of illiquid instruments, because the pricing discrepancies tended to be larger in these illiquid instruments. And then the machines just start making all possible combinations, a finite number of combinations of things you can buy or sell. And at the end, it was giving me a chart like this, basically odds. there is 3 times the 3-to-1 odds. So basically making it like a bet. And you set a threshold. Just show me things that are 5-to-1. Or maybe there is none. You just wait here. And the thing is that you have to act fast. So you trust your code, you just take the trade. And it did work a lot of the time. So a lot of heavy use of parametric distributions and empirical distributions, optimization programs. 1998 to 2008, that's when things started to get a little more interesting because I started to work with different data sets, not just price and volume for securities. But I started working for AIG, and they insure anything, or they used to insure anything. So again, a client comes, this satellite is going to go to space, and I need insurance. How do you price that? If you ask a finance guy, quant, he doesn't know because that's not what we do. But then you start talking to these people in insurance side, and brilliant actuaries, mathematicians, statisticians, maybe they don't know how to program. And then you start combining all of this knowledge of these guys with your own knowledge, and all of a sudden you're pricing that kind of risk. And then we get a client that says, you know what? I'm running a theme park in Florida. And in the summer, I have had some revenues that were below expected because there was rain. And when there is rain, people don't go to the park. So is there anything you can sell me to protect against that? And again, it's a fascinating problem, but how do you do that? Again, data science. It's just not called data science back in '98. So you have historical data for precipitation, and you have the revenues for this specific theme park, and you have external data sets that you can add, and you can come up with a price. The interesting thing is that when you start then adding finance to the mix, you realize, wait a second, this event has negative correlation to another place in the world. And you test for causality and all of that, of course. And then you realize, wow, if I could say similar instrument in the other part of the world, or in the other side of the state, or whatever it is, I could make free money here. And then that's a new market that came out of that, weather options. So it was very fascinating to deal with this. And then these are real data science deals, basically. So I don't know if you ever heard of the Bowie Bonds, as in David Bowie. David Bowie, I'm sure you know who he was, had some financial issue a few decades ago, years ago. So he needed some loan, I don't know, $20 million, I don't even remember. So the thing is, he can sell some of his assets to get $20 million, or he can go to a bank and ask for a loan. But is there a better way? And the better way was this, financial engineering with data science. So let me see if I can show. This curve shows the volume of sales of let's say, a record or a movie when it's first released. When the thing is first released, you have all these high sales. And, they happen in seconds or in months or in weeks, but this is the shape. And then after X period of time, they tend to level. And when you release a new content in the web, you have a lot of activity initially, and then people get bored and they don't watch it anymore. Same thing. So you can actually parameterize that. And the thing is that with David Bowie, he had a bunch of songs that he had issued, and each one of these songs had a curve like that. So if you aggregate all of these curves, you could have a very predictable, quantifiable sum of residual value for each of these songs. And actually, there are things you can do to bump that again. I'm not going to explain how you do that, but re-releases or new technology. But the thing is that with financial engineering, you could capture all of those future flows that have some uncertainty and transfer. Let's give you an example. Let's say he was receiving $2 million per year. For the next 10 years, for the next 25 years, it's $50 million or something like that. So now you create a structure where you give him $20 million in exchange for those $25 million that are going to happen in the future, if they happen. So it's fine, because he gets to receive that money right now. But all these future flows are now for the benefit of a group of investors, put it that way. So these are a group of people that want to diversify their income, their sources of income, and they see this as an interesting thing. So that's more or less a topic. There is a lot of stuff going behind this. But when I saw that, and I started to do, wow, so let me start doing the same calculation for all of these guys. So we have Elvis Presley, John Lennon, et cetera, et cetera. At the end, I came up with an expected return for the state. Usually, we're talking about dead composers, So the state, the relatives or whoever receives the flow, sort of find these sort of things attractive. And depending on the actor, like for example, Tupac Shakur has a lot of volatility because some years have good sales, some years have bad sales. This other guy here, George and Ira Gershwin, have very little volatility. They are composers that do a lot of Broadway shows, or a lot of Broadway shows use their music. So this is the kind of thing that quants have been doing. It's very related to data science. But it's not just the quantitative elements. There are also qualitative. So you have to work with lawyers to put together structures to try to cover all of the risks. Data scientists work ends with the model. And here's what we do. But how do you make it better by using qualitative elements? And that's part of the job of a quant. Also with lawyers. So from there, I started to apply some of the same logic to movies. And movies is very interesting because the typical way that Hollywood finances movies is, well, if it's a Spider-Man or one of those big productions, they use their own capital. But sometimes you have small films, or not so small, that it's a great story, and it had Angelina Jolie or Brad Pitt in the script, and it's an action, whatever it is. And it's not that kind of movies that is the bread and butter of the studio, but they like that. So what happens with those sort of movies? Well, those movies are typically funded by creating a new company. So it's New Movie LLC. And that company goes out and raises capital from wealthy people. That's it. Some rich guy, hedge fund manager, or whoever that wants to have exposure to that. And they think, I think this movie is going to be great. That's it. It's just very, it's a gut feeling that the movie is going to be great. There is no quantitative assessment because there's no way to quantify a creative asset. But this is what I did. I started to grab as many data points I could. I scraped every single website that talks about movies and actually started to create a database of movies since 1900. Obviously, very sparse in the beginning, but in the 1970s, it becomes very populated. And then you have actors, genres. I had to develop my own taxonomy to classify movies. This is action. This is romance. And once you have that, you start creating machine learning models and do it in sample and out of sample and see how it does. So these are some of the features, like the rating and the genres. And these are some of the out of sample results of things I was doing. And so it looks good, predicting or forecasting one single movie was very risky, but a portfolio of movies becomes very stable. And the next thing I know, I'm talking about this in Hollywood and meeting a bunch of cool movie stars. I remember being in all of a sudden I'm in this party with the cast of The Fast and the Furious, and I'm like the financier guy, and I'm just a quant guy. But it was fun. That was a fun time. So if you want to learn more about this, because I don't have time to explain everything here, just Google that. And I wrote in a blog a long time ago how this whole process went. And then I started to use the same concept, but for these sort of things: earthquakes, hurricanes, weather, windstorms. And I'm just going to go fast. But it's basically, wherever you have a ton of data, like earthquakes, there is data for earthquakes that date back, hundreds of years. And although it's more accurate from 1970s to now. And you have data for, at least in Italy, for example, volcano eruptions that dates back to 2,000 years. And this is an actual deal that it's kind of interesting because this happened for Tokyo Disneyland. Tokyo Disneyland, you all know Tokyo Disneyland had a problem because they were trying to insure the whole park against an earthquake in Tokyo. And the quotes that the insurance market was giving, that was super high. Is there a way to bring down that cost? And the way to bring down the cost was to come up with a new structure, which is basically this parametric deal. So you have a circle of X. It was what, 10 kilometers, 50 kilometers, or 75 kilometers around the center of Tokyo Disneyland. You define the latitude and longitude, and then you define a table like that. So the table says that if the earthquake is 7.9 or greater, there is 100% loss of principal to investors. But if it is 6.5 and it's in the outer circle anywhere, epicenter, there is zero loss. So that payout table, which you had to design, by the way, is not given to you. You had to do a lot of iteration. Sort of correlates with the losses in simulation, correlate with the losses that will happen to Tokyo Disneyland if an earthquake happens. So that took a lot of iterations for me to do these sort of things. But later on, I updated all that old code, and now I'm able to do that like in seconds. Things that used to take a week. 10 years ago, 15 years ago, you can do in seconds now. And this is the same concept of Tokyo Disneyland, but applied to volcano eruptions in Italy. And again, I came up with this index, which is, instead of like the magnitude of the earthquake, in the case of Tokyo, you have this thing called volcanic explosivity index. It's the same thing. And this is an actual deal that was put to the client. So if you want to learn more about this, just Google that, and you can see a whole, I think it's 1 hour presentation just going through the code to do this. And this is just a very quick summary of how I had been using data science. And at this point, we're in 2008. Everything was really good. I started to work in Lehman Brothers, and I was in charge of a lot of this cool stuff, and this is one of the things that was in the works, We started to use that Bowie Mold to evaluate some potential deals, but then everything was going to be put in a vehicle and sell to bondholders. And I say almost because, there is no sound here.
Bankruptcy.
Yeah, it's just 2 minutes so you get an idea of what happened. This was 3 weeks ago.
Hi, my name is Loveleen Sidhu.
William Putz. Mohammed Karim.
Lynn Gray.
Luis Sanchez.
Beth Annisman.
1 week before the US Open was taking place. And a lot of senior people were there watching the game, and I was there. That was a very interesting week. Bear Stearns had collapsed, and the next ones in line, Lehman Brothers, we never thought it was going to collapse, but the talk among some of the clients there in the suite was the bank was not in very good shape.
There certainly was, all throughout the spring and summer, feeling that somehow the senior executives would find a way to hold.
But you want to see more about this. It's actually one of the best things that they have done about the whole collapse of Lehman Brothers, because it talks about the human point of view. Is what happened to the people. Most of the things you see out there just deal with the macro issue, but this one was actually what happened with the people there, what we were doing, and what are they doing now. Anyway, so up to the point, this is a sample of actual deals that went out that use data science. So, but in total, I don't even remember, it's more than $5 billion. So this is the thing. Data scientists have been around for a long time, and they have been using neural nets, but they have been working for hedge funds and banks, and they just don't talk about what they do because they are highly proprietary deals. And so this goes a little bit in line with what Fabio was saying. You know, there's not a specific path to becoming a data scientist. I happen to just evolve into a data scientist. And I have met some PhDs. Actually, I work very well with the PhDs because I'm more of the left side of the type of data scientist, more like the business and creative, where I deal very well with the research type of data scientist. So investing in the stock market. I see, are we okay with the time? Okay, so 2010, took a break for the Lehman thing. In 2010, I started my prototype semantic search engine, a deal search engine, and social media search. And like I was saying before, the main thing there was this new algo called Content Rank. So I was approached in 2014 by this hedge fund that wanted to get some of the data I was collecting. And so let me explain this a little bit so you understand how machines are starting to do a much better job than human analysts at this game. This is a very simple example. Groupon, everybody knows Groupon. This is what's called the balance sheet, a very summarized. So that number that says top line revenue, that is what every analyst, highly paid analyst that work for Wall Street firms is trying to guess. They're trying to guess that for Apple. They're trying to guess that for Amazon, every single company. If you get that number right, you may be able to make a lot of money. But you make a lot of money when you get the number right and the others get it wrong. That's when you make money. So top line revenue is that, how much it was sold in this quarter. Below that, you have a bunch of stuff that doesn't move that much. Okay, so like, you know, the cost of people, the operations, the rent, that doesn't change that much. But what you sold, that is the big surprise. And at the end, all of that gets translated into this number, which is the earnings prorated by the number of shares, and it's called earnings per share. It can be positive or negative, or flat, of course. So they are very important because that's how companies, at least in the US, disclose how well they did. It's a very regulated industry, the securities industry, right? They announce this every quarter, but there is a lag. There is a lag that can be as high as 90 days between the end of the quarter and the moment it gets announced. Okay? And these are the positive cases, you know. Positive earnings, negative earnings. You can have a negative surprise or a positive surprise. So that depends if you got it right and the others got it wrong, or you got it wrong and the other got it right, or whatever the case is. Now, I started collecting data. Let me see if I can, yeah. For how well collectively these highly paid analysts were doing. And it looks like, at the moment I stopped doing this analysis, as we have more data, there is more getting it wrong than getting it right. So there is something going on here. As we have more data and we have more machine learning, instead of getting it right, they're getting it more wrong. This is what's fascinating. So this is what happened. I started to think, cool, group of machine learning things forecast that and do a better job than Wall Street and hedge funds. And this is what happened. Actually, I started to think about that question after I figured out how to do it. But it was a total accident. So these are the 3 search engines I launched. The social search, the one that does deals, and that one that does semantic search. I'm going to tell you how I got to it by accident. So I'm going to play this video because this doesn't exist anymore, this app, but I'm going to show you what it used to do. Okay, so this is what's happening here. This particular search engine was targeting the deals market, like Groupon, daily deals, last-minute deals. So Google tried to acquire Groupon, but they rejected the offer, and it was a good offer at the time, but then Groupon leave as an independent company. And after that, a lot of other companies started to do the same, leaving social and Amazon deals. So all of a sudden, you have a huge segmentation in the market because the daily deals are being captured by about 130 companies all over the world. And depending where you were or who was giving you the deal, you can find the same deal from 2 different providers, and one was better than the other. But you didn't know that because Google is not going to tell you, oh, Amazon has the same deal cheaper. They're not going to send traffic to Amazon and vice versa. So I saw this as an interesting problem to solve. And what I did is I just started to collect all of the data, all of it, for each one of those guys. Let's call it high-frequency scraping. And I was putting all of this in a database, and then I had machine learning code that was disambiguating the deals. Oh, this deal is the same as this deal. So the credit goes to this merchant. And I'm just doing all of that automatically. And so when people come to this app or the website, it finds your location, and it tells you what deals are around, depending on what category you choose, meals or retail. And it tells you, here are the best deals. You don't even care who is sending you the deal because you just want a deal. But when you click on the deal, then you see it's coming from Groupon, it's coming from Google, it's coming from whatever. So a friend of mine who has stayed in the investment banking business said, Groupon is announcing earnings in 2 weeks. I think you can figure out what the top line revenue is. And I never thought about that. But he was right. It was 2 weeks for them to announce. That's a big number that Wall Street is trying to guess. But I went to my database, I isolated Groupon, and I had exactly every deal that had been sold because I was scraping everything. It's right there. The information is in front of you. So when I did that, I came up with a number. I accumulated the values. You have this. And I see, wait a second. This is a lot less than what Wall Street is expecting. Wall Street is expecting $600 million or something like that. But my data show that they only sold 500 million. They think it's going to be 600, but it's 500. So I did a back of the envelope calculation. I came out with like minus 8 cents. But meanwhile, you look at big hedge funds, and let me see if I can go there. Like Tiger Fund Management and others were expecting, I think it was 8 cents per share positive. And my data says -4. So the announcement came, and it came -4. So I said, I just stumbled upon something back into finance without even realizing what I was doing. So I started to apply this model to Groupon and other companies, et cetera, et cetera. Right after this hedge fund came and invested a little chunk of money in my company. And then I kept developing stuff. And more stuff came out of that. But I wanted to get to this point because this is actually the thing that is probably generating the least amount of money for me, but it's the one where I have the highest satisfaction. So that's what I wanted to show you. It's very interesting. And it's a little connected to the previous talk about neural nets and all of that. So this is the thing. When I was a kid, I heard something called the Goldberg variations by Bach. I don't have any background in music or anything, but I really like this, and I always wish there were more Goldberg variations. But that's it. We only have what Bach composed. But as an intellectual property asset, it's very valuable because, there are only 30, and there's 0 probability of having more because this guy is dead. And aside from 0 probability of having more of this, it's a difficult piece very difficult piece to play in the piano. Anyway, so I learned about this Professor Cope. So this guy is a genius. He's one of the pioneers in the use of artificial intelligence for creativity. But he specializes in music. And he actually came up a long time ago with an AI as a tool to help him in the creative process. Somebody had commissioned, I think it was an opera, and he was like years without composing anything. So he started to think about, maybe I can write a program that helps me in the creative process. And eventually he did create something, and call it Emmy. But then, the Emmy, the music company, sued him or threatened to sue him because he was using the same name. It became a little hard. But anyway, he has a workshop, or had a workshop in the University of California, Santa Cruz, for people with musical background, where he basically tells them, when you're stuck in your creative process of composing music, you can use some of this stuff to help you get unstuck and compose more. And I was fascinated by that because in my mind, if I could just find a numerical representation of music, then I think I know what to do. I think at least I thought in my head I had created a semantic search engine, maybe some of the same stats and math applies. So I wrote to him. I said, I don't have any background in music. I don't know how to play anything, but I know data. And I thought he was never going to accept me. But then eventually he wrote back and said, you know what? I'm going to do an experiment. Just come to the class. I'm going to skip this. And what I found is that by day 3, and this is very intensive, 3 weeks from 7 a.m. to midnight, and there is a lot of coding. By day 3, I'm just ready to give up because it is Lisp, and I don't program Lisp. I program in Python, and also I don't have any background in music, so these guys who have music background, some of them PhDs, are talking about rotations and octaves and things that I don't understand. So I asked him, look, this is very difficult, but if you let me use Python, maybe I have a fighting chance, because otherwise I need to leave. This is just too advanced. And that's what happened. So once I started to use familiar tools, the concepts were still complicated, but I was able to get to this. So basically, imitation. You can read that. this is what I found. This is what I found. This is at least my theoretical thinking. If I start analyzing the music of these guys, maybe I find common elements in their music, which I call it, for lack of a better word, cluster of musical structure. And then I started to see, wow, these elements are common here, here, and there. And I started to grab some of those elements. And I started to see that, you know, a lot of this intelligence doesn't happen in isolation. Everything we do, we learn from somebody else, or we get influence from somebody else. And this is exactly what happened in music. So the first thing, a little program. It's not actually a neural net, but it's machine learning that giving a lot of examples of baby lullabies creates something that is like a baby lullaby, but it's completely original. And these are the things that came out. I'm just going to play a couple. And another one. Oops. So that's the idea, and then progressively, but in a very compressed time frame, give more complicated stuff. So this is one that experts in music say, wow, I never heard that thing from Mozart, and it's not Mozart, it's just an AI. You get the idea. And then more complex, you know, okay, take this song and create something that sounds like that, and the same thing. And I'm just going to skip it. And this is very nice. Now, like a portfolio. In finance, you have portfolios of stocks, and the portfolio tends to be more stable than any single stock. So I said now, okay, mix all of these styles. Let's see what comes out. And this is a jazz that people listen to it. They say, wow, I cannot believe that's a machine that composed that. And this is very difficult because jazz doesn't have much structure. So it's actually one of the most complex things to do. Anyway, so you get the idea, and now the machine can just do anything. Freedom. You don't tell it anything, just compose. And then it tends to compose very long pieces, but this is one free-form composition. And even techno music, but that's a little more collaboration with a human. Anyway, so the idea here is that, you know, it's starting to be like a Turing test, at least for music. You play these things and people cannot differentiate between a human composer or a machine. You can Google algorithmic arc quadrivium if you want to join my meetup group where I talk about this. The problem is the business side of this. When you compose a song and you put it out there, you collect royalties, or your estate collect royalties 70 years after the death of the composer. And after 70 years, it goes into the public domain. So what happens when an AI is creating the song that doesn't have an end date? So that's a problem right now. You know, you can listen to this song in Spotify, Apple Music, and it's all under my name because I cannot register an AI as the composer. So I'm just a regular, very prolific composer, you know, but I don't do anything. I just push a button and I get the songs, and I get paid royalties. So this is my contact information. If you want to hear more about this or any of these topics, just contact me there. And that's it.
Any questions for Luis while he's still up here?
What website do you use for data scraping?
No, you had to create your own scrapers. Yes. So you, I'm sorry? No. I use Python for everything. So you just had to code your own scraper. And the best tools are the ones you create yourself, and you're relying on a third party to do data collection or do training. It's not wise business wise, because Python. So you can do a lot with Python. So.
Anything else?
Have you actually fell in love with any musical instrument after you started composing music?
Yeah, I think piano,